Welcome to my problem solving class of Advanced Microeconomics. Today we are going to solve problem set 2, utility and demand, and this is chapter number 2. Let's start our solution. 2.1. First problem is about finding Walrasian demand for CES utility function. Consider the following CES utility function. First question is find Walrasian demands x1 and x2. Second, what is the Walrasian demand when parameter rho tends to 0? Now consider a variant in the above utility function. We have to show that when rho equals 1, indifference curve becomes linear. When rho tends to 0, indifference curve represents a Cobb-Douglas function. The exponents satisfy alpha plus alpha 1 plus alpha 2 equals 1. So the indifference curve looks like this. The above indifference curve was straight line, and the second indifference curve looked like this. And the third question is when rho tends to minus infinity, this indifference curve becomes right Leontief utility function. U x1 x2 equals min x1 x2. So our utility function could be look like this. That means the indifference curve is L-shaped. Indifference map combines L-shaped indifference curve. Now let's move to the solution. First question is find the Walrasian demands x1 and x2. So first build a Lagrangian for the UMP. UMP means utility maximization problem. So let's take a first order condition FOC, and FOC with respect to x1 is the first equation, second equation is with respect to x2, and third equation is with respect to the Lagrange multiplier lambda. Rearranging the first two equations, we obtain the Walrasian demand for good 2. And plugging x2 into the budget constraint, we get this equation. And solving for x1, we get the Walrasian demand for good 1. So we can list Walrasian demand for good 1 and 2. So these two equations are complicated. We can make it simple by using rho upon rho minus 1 equals r. I mean replacing rho upon rho minus 1 by r, and then we get this Walrasian demand for good 1 and Walrasian demand for good 2. Now question B says what is the Walrasian demand for good 1 and 2 when parameter rho tends to 0? And it is very simple, because if we make rho tends to 0, that means know that r equals rho upon rho minus 1. So when rho equals 0, then r should be equal to 0. So if we apply this in the demand equation, Walrasian demand equation, x1 and x2, we get xi, that means I equals 1 and 2. So this is our Walrasian demand when rho tends to 0. So when rho tends to 0, we insert the values for value for rho, and we get this equation. And this equation is simply Walrasian demand for consumer with Cobb-Douglas utility function u x1 alpha, x2 alpha, x2 1 minus alpha. So if we take this as utility function, so from this utility function we can get two Walrasian demand. One is x1 equals w divided by 2p2, and x2 equals w divided by 2p1. Okay, and the if we look at the utility function, this is Cobb-Douglas utility function. We know the Cobb-Douglas utility function is a general form. So u x1 x2 means a x1 alpha, x2 1 minus alpha. That means it is a constant elasticity of substitution, because alpha plus 1 minus alpha equals to 1. So it is the form of Cobb-Douglas utility function. Here you see that here a equals 1 and x1 and x2 remains the same. So this is our Cobb-Douglas utility function. So when we put a rho equals 0, we get the Cobb-Douglas form, say that which exactly coincided the Walrasian demand of a consumer with Cobb-Douglas utility function, where alpha is greater than 0. Now we are with C. Problem 2.1c says we are here with variant of CES, constant elasticity of substitution, u x1 x2 equals alpha 1 x1 rho plus alpha 2 x2 rho to the power 1 upon rho, where rho is not equal to 0 and rho is less than or equal to 1. So if this is the variant of the above CES utility function, we have to show that, number 1, when rho equals 1, indifference curves becomes linear. Okay, that means good 1 and 2 are perfect substitutes. That means when rho equals 1, the utility function becomes u x1 x2 equals alpha 1 x1 alpha 2 x2. So this means that utility function becomes linear and goods are perfect substitute, and this is only when two goods are perfectly substitutes. And the equation of an indifference curve can be obtained by solving x2 so if we solve this one, so u upon alpha 2 minus alpha 1 upon alpha 2 x1. So for instance, if utility equals 10, the linear indifference curve originates at 10 upon alpha 2. That means cross x-axis at, so if this is x1 axis and this is x2 axis, so this point is 10 upon alpha 1 and this point is 10 upon alpha 2. Now the second part of 2.1 C2, when rho tends to 0, when rho tends to 0, the utility function represents a Cobb-Douglas utility function like this: u x1 x2 equals x1 power alpha 1 x2 power alpha 2, and the exponents satisfy alpha 1 plus alpha 2 equals 1. So this is our reminder. So if we put so let's define u curl x is ln log natural ux. So from the remainder equation we get this one. So u x1 x2 equals alpha 1 x1 rho plus alpha 2 x2 rho to the power 1 upon rho. So if we take log of this, I mean natural log of this, we get this equation. And then we take limit, because it says that it is not that rho equals exactly equals 0, it is rho tends to 0, so we should apply limit function. Okay, and we see that when we apply limit function, then it becomes indeterminate. So we need to apply L'Hopital rule, because when 0 upon 0 it is indeterminate. Okay, so applying L'Hopital rule we get this equation. So L'Hopital rule means you take first derivative of both numerator and denominator. ddx of numerator and denominator. Okay, so taking this, we get this equation, and this ultimately cancel out 0 by 0 indeterminate position. So we get this, and now we can insert the value of rho and get this equation. Okay, so this is because in our condition we say that alpha 1 plus alpha 2 equals 1, so that's why this is the value of ux. So u curl x is now equal to x1 to the power alpha 1 plus x times x2 to the power alpha 2. Okay, and solving this for x2, like the previous one, we get this one. So when this is both alpha 1 and alpha 2 is equal to 0.5, that means 0.5 plus 0.5 equals 1, then indifference curve becomes x2 equals u curl square upon x1, and this indifference curve is decreasing in x because x is in the denominator, but at a decreasing rate. So we can say that this the indifference curve is bowed in towards the origin, that means convex to the origin. Now what about when rho tends to minus infinity? Question number 2.1 C and sub question 3. When rho tends to minus infinity, the utility function becomes Leontief utility function. That means ux x1 x2 is minimum of x1 and x2, and thus represents two goods are perfect complement. So question number 1 was perfect substitute, now it is perfect complements, and question number 2 C2 was bowed to the origin. So here is our limit function. We need to show that if x2 is greater than or equal to x1, that means x1 is mean, then the limit function is equal to x1. If we can show this, then we can prove that this limit rho tends to minus infinity creates a linear, Leontief utility function which is L-shaped. Okay. All right. Suppose that x2 is greater than or equal to x1, that means x1 is minimum, then we can x2 to the power rho is less than or equal to x1 to the power rho, because we know that rho satisfies not equal to 0 but less than 1, and because it is approaching minus infinity, so it takes negative number. So if a rho is negative number, then the inequality reverses, and when a rho is in the power. So if we multiply this by alpha 2, positive alpha 2, then it yields alpha 2 x2 rho, x2 to the power rho is less than alpha 2 x1 to the power rho, and then we add alpha 1 x1 to the power rho on both sides of this inequality and get this inequality. Okay, and we can rearrange this. So alpha 1 plus alpha 2 in one side and x to the power rho, and since rho is a negative number, so we can revert, like previous, we can revert the inequality sign, here, and let's call it as the left hand side is B and the right hand side is C. And when x1 and x2 are both positive, and we can say that 0 is alpha 2 x2 to the power rho is also positive, and if we add both sides by alpha 1 and alpha 1 x1 to the power rho, on both sides of the inequality we obtain this one. So obtain this one from this, and by adding this one to both sides, and again if when rho is a negative number, so we can reverse the sign and then get, and look, this is actually our left hand side equation of the equation number 1b. So we can find a combination of these two expressions as this one. So we can say that A is greater than or equal to B is greater than or equal to C. Okay, so this is our equation number 2. So we can now apply squeezing theorem to the limit function, because our target is to find the limit of this equation rho tends to minus infinity. So why squeezing theorem? Because if we can find the limit of this a value and limit of this same value, then we can say that it is also true for the limit of beta, limit of B, because B is lying between A and C. So the value of the limit for A and the value of the limit for B and C is also the value of the limit for B. This is squeezing theorem. So we can apply squeezing theorem in the limit. So the first limit is limit rho tends to minus infinity alpha 1 x1 rho 1 upon rho. So if we make simple, then it is 1 by, so it can be written as alpha 1, so 1 by alpha 1 by 1 upon rho x1, rho and rho cancel out, so x1, and we know that 1 by rho is 1 by minus infinity, which is equal to 0, and anything to the power 0, alpha 1 to the power 0 equal to 1, so we can get this one as x1. Okay, so we now find that limit function, so limit function in A yields the value x1. Now what is the limit function, limit of a term C? Similarly, the similar way we can say that this to the power 1 rho and rho cancel out, and rho 1 upon rho is equal to 0, and 0 to the power this equal to 1, so it is x1. Okay, so two same values for A and C, same limit value for A and C, and for this reason we can say that B, the limit of the term B is also x1. Okay, so limit of this is also x1, and this is what we needed to show if x2 is greater than or equal to x1. So if x1 is minimum, then the limit of this is minimum mean of x1 and x2, which is x. So applying limit, we get this result. Case of x when x2 is less than or equal to x1. So when x2 is mean value, so the limit of this is equal to x2. Combining these two results, we can say that when rho tends to minus infinity, the utility function u x1 x2 turns to alpha 1 x1 rho x1 to the power rho plus alpha 2 x2 to the power rho whole to the power 1 upon rho becomes a Leontief utility function. U x1 x2 equals minimum of in x1 x2. So when x is minimum, then it is equal to x1. When x1 is minimum, it is equal to x1. When x2 is minimum, it is equal to x2. And this is L-shaped Leontief indifference curve for two complementary goods. All right, so this ends our problem 2.1. Let's move to problem 2.2. Problem 2.2 is about Walrasian and Hicksian demands. It says, suppose that preferences are represented by a Cobb-Douglas utility function again. U x1 x2 equals x1 alpha x1 to the power alpha x times x2 to the power 1 minus alpha. The utility function is increasing at all x1 and x2 strictly positive and homogeneous of degree 1. The consumer faces P1 and P2 at, as prices for x1 and x2. Now the question is, formulate information set for utility maximization problem UMP and expenditure minimization problem EMP. Next question is, calculate Walrasian demand functions and derive indirect utility function from them. Next question is, calculate Hicksian demand functions and derive expenditure functions from them. Now the solution. UMP is very simple, maximization of the objective function subject to the budget constraint. Utility maximization problem UMP, expenditure minimization problem is, if it is primal, then it is dual. So if one is maximum function, the dual should be minimum function, and now minimum function, we minimize the budget function by, or we minimize budget line, or we minimize budget subject to the utility function. So these are actually same problem, one is maximization and other is minimization. If this is the case, so we have to find from the indifference map and the budget line, we have to find this point by UMP. So this is called indirect utility function. So max u, and if we have several budget line, so we need to find minimum possible expenditure function. So this is mean expenditure function. Okay, so if we take the question B, then it says that derive indirect utility function, and first derive valuation demand x1 and x2, and indirect utility function, that means the maximum value function. So it is actually maximum value function or indirect utility function, and this indirect utility function is this utility function, which is tangential to the budget line. And C says about calculate Hicksian demand function, that means H1 and H2, and derive expenditure function, and this expenditure function is the minimum value function. And this minimum value function is the budget line that is tangential to the optimal utility function. Okay, so okay, now question 2.2b, valuation demand function and indirect utility function. So we set the Lagrangian from the UMP. This is our Lagrangian, and setting the partial derivatives, that means FOC. These are all FOC, first order condition, and first derivative of utility function with respect to x1, first derivative of utility function with respect to x2, first derivative of utility function with respect to Lagrangian multiplier. So dividing 2 by 3, we get this equation. So from this equation we get the x2 equals this. Substituting this x2 in the into 4, that means the budget function, we get the value for x1, which is this one. So we get 2 valuation demand x1 and x2, and we can form indirect utility function by substituting these valuation demand functions back into the direct utility function. So our direct utility function was u x1 x2 equals x1 alpha and x2 1 minus alpha. So here x1 is this and x1 is that, and we know this this is the value we in the last slide we have seen. This is the value for x1 and this is the value for y1, and putting this into this equation we get the maximum value function, which is also called indirect utility function. Now 2.2c, which is about Hicksian demand function and expenditure function. Again we set the Lagrangian for EMP, expenditure minimization problem. So this is our Lagrangian function for EMP, and setting partial derivatives for FOCs, we get equation number 7, 8 and 9. Again by dividing equation 7 by 8 and simplifying this, we get x2 equals x1 1 minus alpha p1 divided by alpha p2. Substituting x2 into 9 we obtain, and simplifying this we get this as x1. So we have got two values for x1 and x2, and these are the Hicksian demands for good 1 and 2. We can so we get these two for good 1 and 2, and this can be converted into standard Hicksian demands, and this is our Hicksian demand function for good 1, and this is our Hicksian demand function for good 2. So we can form expenditure functions by substituting these two Hicksian demands back into the objective function of EMP, that means the expenditure function, that means the budget line. So our expenditure function is function A becomes, so what was our budget line? Our budget line was P1 x1 plus P2 x2 equals W. Okay, so here x1 is actually h1 because of the name Hicksian begins with h, and this x2 is h2. So if we put the values of x1 h1 and h2, we get this expenditure function, and simplifying this we get this equation, and finally this equation. Okay, similar to the UMP, from EMP we get the expenditure function, which this expenditure function is actually minimum value function from EMP. This ends our problem 2.2. Now problem 2.3, checking WARP. We have three demands: random demand, average demand, and conspicuous demand, and we are going to see whether they satisfy WARP. So let's move to the solution. So what is random demand? For any pair of prices P1 and P2 and wealth W, if consumer randomizes uniformly over all points of the budget frontiers, that means this is our budget frontier, and if the consumer randomizes any value from on the budget line. If consumer randomizes uniformly, that means he is totally unbiased about the position of the point. So why random demand arises? Random demand arises when consumer regards two goods as perfect substitute. So we know that for perfect substitute, our IC is straight line, and it is a following pair of the price ratio, and which is equal to the marginal the ratio of marginal utilities. So when we get this indifference curve, we are actually obtain by UMP, we actually obtain a straight line, I mean demand curve like this. And if this is the case, if the price ratio maintains marginal utility of x1 upon marginal utility of x2, the continuum of Walrasian demands emerges along the budget line. So there was a continuum of Walrasian demand emerges along the budget line. Why? Because consumer is indifferent among all points on the line, because they are perfect substitutes. So he is indifferent, and because he is indifferent, he can randomly choose any point as optimal bundle. So we can express this in the graph like this: random demand. So let's prove that this demand function doesn't necessarily satisfy WARP. Okay. So what is the definition of WARP? WARP says if the new consumption bundle, this one, is chosen under the new price and wealth. So new price here is P prime, and new wealth is W prime. So if this is the bundle is affordable under the old price, so this is old price, so this is affordable bundle, new bundle but old price. If it is affordable, that means less than or equal to W wealth, and new price bundle is not equal to old price bundle, then it is obvious that so then if the old, then it must be the case that old consumption bundle, this is old consumption bundle, old bundle is not affordable under the new prices and wealth. So if this is affordable, then the old bundle at new price should not be affordable. That means this inequality over new wealth. If this is the case, then we can say that WARP satisfies. So in case of the random demand depicted in figure 2.1, we see that this is the case, this is true, and this is the condition, but we see that the old bundle at new price is also affordable. That means this sign. Why? Because you see that old consumption bundle is still affordable under new prices. So this is old affordable bundle and this is new price. So this bundle is under the dashed line. That means P prime X P W is less than W prime. This is W prime. And this one is also affordable. So if this is the case, then WRP violates. Simple as that. So there exists a positive probability that random demand assigns bundle as the one illustrated in 2.1. So we can conclude that the random demand doesn't necessarily satisfy WARP. Now let's take 2.3b, average demand. So what is average demand? It is nothing but the expected random demand, okay, given P1, P2 and W. We saw that random demand arises in the presence of perfect substitute. The average demand, on the other hand, emerges as the average bundle that consumer selects after randomly choosing a bundle from his budget line a sufficient number of times. If the randomization is sufficient in number, then we see the emergence of average demand. So if we take the expected value of random demands, we get the average demand. So expected random demand is allocated at the midpoint of the budget line. So when we take the expected value, so it is obviously the midpoint of the budget line, which is depicted in figure 2.2. All right. So let's now prove that WARP is satisfied for average demand. To prove, let's work with contradiction, proof by contradiction, and assume that average demand violates WARP. So we can find two possibilities that might violate that violation might take place. So you see that this is the random demand midpoint, okay, and the position of x1 prime and x2 prime in panel A and B, where WARP might be violated. So you see that in both figure, new bundle xp1 p prime w prime is affordable under old prices. So here is our old price. So this bundle is for old price. This is P1 P, and which is this bundle. The new bundle is lying below the red line. That means old old bundle with old price, but the bundle X is also affordable under the new prices. So when we take the bundle X and new price, so this line is with new price P prime, so this is also affordable under this. So if it is affordable, that is, if it lies on or below the new budget, that means dashed line, so here we can say that WARP violated. Okay, this is for this panel, this left hand side graph. What about for the right hand side? Same thing. Under the I mean this point is under the red line, that means old budget, new bundle. So under means affordable, and if old price is also affordable under the new budget, then WARP, that means this point is lying below the dashed line, so here also WARP violated. Now we see that WARP was violated in both cases. When we take the argument, contradictory argument. So let's first examine whether these are true. So first determine the location of x1 and x2, x1 and x1 prime. So old, I mean point, location of points x1 and x1 prime according to the average demand. Recall that these points must be located at the midpoint of the budget line. So in order for both points to be average demand, they must be in the middle point of the both budget line. That means x1 equals half W divided by P1, and x1 prime also half W prime P1 prime. So both should be half of the budget, half point on the budget line. So if we simplify this, we get the 2x1 should be equal to 2x1 is equal to W divided by P1, and 2x1 prime equals W prime divided by W prime upon P1 prime. Also we can see that figures, both figures, x prime is less than x1. So here is x prime and this is x1 prime and x1. Therefore double of these 2 points should also be less, which implies that W prime upon P1 prime also less than W prime P1. But in both figures actually we find that W prime upon P1 prime is greater than W upon P1. You can easily see this. This one is less than this one. This one is less than this one, which contradicts the one we have got by the logic of contradiction. So that's why we say that our assumption of violating WARP was not true, so we can say that average demand cannot violate WARP. Now let's go for the conspicuous demand. What is the definition of conspicuous demand? When individuals spend all of their wealth on most expensive goods such as luxury goods, then their consumption is called conspicuous consumption. For instance, if good 1 is the most expensive, so P1 is greater than P2 in case of our two goods condition, then consumer spends all his wealth on good 1. So here's the definition of demand for conspicuous demand. If consumer spends all goods on this if Pi is greater than Pj, j is not equal to 1. If the case is that Pi is less than or equal to Pj, then the condition is that it is he or she is spending 0. Okay, so let's divide it into two cases. Case 1, when P1 is greater than or equal to P2, and case 2, when P1 is less than P2. Okay, so let's check WARP satisfied or not. So for case 1, when P1 is larger, then consumers spend all goods on P1. So you see that our bundle lies on the horizontal axis with W, all amount of money on W upon P1. So the point is here. In case 2 is the reverse one. So spend all amount of money, and the demand is on the vertical axis, x2. Spend all money on good x2. So 2.5 represents the both case simultaneously. So if we add, or if we connect the 2.4 and 2.5a, we get this figure 2.5 represents the combination of the previous two figures. Budget line B PW represents the higher price for P1, while the budget line B P prime W prime depicts the opposite case, where P2 is the high relative to P2 is high relative to P1. So after depicting the bundles that represent a conspicuous demand for all price vectors, we can check if WARP satisfies or not. So this is the definition of ARP we have mentioned in the in part A. So for that case, the bundle X P prime W prime is affordable under old prices, since it lies below the solid red line. So this is below, so it it is affordable under the old price P. So this is with P and this is with P prime, so this is affordable, less than or equal to W. And bundle XP is still affordable, so this bundle is affordable under the dashed line, that means with price P prime. So we can say that this is not the case, so this is the case. That's why conspicuous demand violates WARP. So what is the intuition? Both bundles are available at PW price wealth combination and at P prime W prime price wealth combination. So the consumer doesn't choose the same bundle under PW than the under P prime W prime, hence conspicuous demand violates WARP. So this ends our problem number 2.3. What about problem number 2.4? This is about substitution effect. Consider an individual with utility function U, x1, x2 and x3 of 3 goods where cross price elasticity is epsilon ij for any 2 goods I and j equal to 0. That means cross price elasticity is equal to 0. Show that the ratio of substitution effects S23 and S13 equals to the ratio of first derivative of x2 with respect to w and derivative of x1 with respect to w. We have to prove that this equals that. This equals that. So in order to do that, let's go for the solution. In order to do that, we note that the substitution effect 2,3 is can be found from the Slutsky equation. This one is coming from the Slutsky equation. The left hand side of the Slutsky equation. Let's see the Slutsky equation. This is first derivative of Hicksian demand with respect to price. Hicksian demand for good 2 with respect to price of good 3 equals Walrasian demand of good 2 with respect to price price of good 3 plus first derivative of Walrasian demand with respect to W wealth times the Walrasian demand for good 3. So it should be good 2. Okay. Note that this term is called substitution effect. This term in this Slutsky equation, this term is called total effect, and this term is called income effect, because this is actually in the wealth or income. And we know that from the problem, we know that the cross price elasticity is equal to 0. So this implies that P3 doesn't affect Walrasian demand for good 2. So change in P3, any change in P3, no effect effect on good 2. That means change in del x2 del p3 equal to 0. So we can simplify now the Slutsky equation. So this equation is the 0, so that's why we just get the simple version of Slutsky equation. Similarly, we can find this from the Slutsky equation. So this is the substitution effect, this is the total effect, and this is the income effect. Okay. Let me go back, and this is actually this was actually right, so 3. So we have got because of epsilon 1 3 equal to 0, that means del x1 pw with respect to del p3 equal to 0. So this one is equal to 0. So we have got simply this one equals this one. So substitution effect equals income effect. So where the second equality also uses the property of cross elasticity. This one I have already mentioned. Hence, the ratio of substitution effect becomes so this divided by this, and common factor x3 cancel out. So finally we have got del x2 dw del w del x1 del w. This is what we have sought. This ends problem 2.4. Thank you.